Okay, so I am starting this session by introducing myself. I am Moina Ghoshal. I am a PMRF at Indian Institute of Science Education and Research, Kolkata, IISER Kolkata, and I have been assigned as the TA for this course, which is entitled as Fundamentals of Spectroscopy, and the instructors were Professor Sayan Bakshi and Professor Anirban Hajra, and this is assignment questions related to week number 9, where there are some discussion about vibrational Raman spectroscopy and resonance spectroscopy, which and I am going to solve you some problems regarding that, which will be beneficial for you to do your assignment. Okay. So all the discussions begin with the introduction of spectroscopy. What is spectroscopy? And as I have mentioned that wherever you go you need spectroscopy, and then we have learned about something called rotational spectroscopy, and then this idea was further modified to from rigid rodent approximation to non-rigid rodent approximation, how actually experimentally these rotational lines look like. Okay, and then we have discussed about vibrational spectroscopy, where at first we have assumed a simple harmonic model or oscillator model approximation, and then we have just changed this simple harmonic approximation of oscillator approximation to anharmonic oscillator. Anharmonic is this anharmonicity term, and then how this is actually behaving in the at practice, we have shown that. Okay, then our discussion then changed to another phenomena, which is spectroscopy, but scattering kind of thing came here, which is known as Raman spectroscopy. And in the previous discussion, I have solved some problems regarding rotational Raman spectroscopy, and the very beginning discussion of Raman spectroscopy was also done. So in this week, I am going to solve some questions for vibrational Raman spectroscopy and resonance spectroscopy. So before moving to further, so I want to show you the same thing for this genius man. Who is he? Do you know him? He is none but C.V. Raman. Okay, so he was a great scientist because yeah. So he is C.V. Raman. Okay, suppose so he was a very great scientist because in 1930 he won his Nobel Prize in physics, because he has first discovered what why sky looks blue. Okay, before that scattering event was not that much familiar, but he has done his experiment with naked eye. Okay, with just naked eye he has in a dark room using sunlight he has done his experiment, and finally gives scattering phenomena, idea about the scattering phenomena that is happening for due for light. It is something matched with the Compton effect, where what you have I have talked to you in the very early stages of these live sessions. So this is the light scattering phenomena. When light is passing through a prism or something, this light, different colors of light are diffracting to different angles. Okay, so they are scattered actually. So in the previous week, we have done some questions regarding this Raman spectroscopy. We have shown that this is nothing but scattering of light. Okay, so we have shown that this is nothing but the scattering of light. Okay, and why this scattering of light happen? For due to when we have started started to show why this is happening, we can correlate this with the quantum, and we have shown that induced dipole is the main reason which is related to this electric field by this relation in mu induced is equals to alpha into E, where alpha is known as polarizability. Okay. So when there is some oscillating electric field, your induced dipole moment will be generated, because when there is nothing, your molecule is in a stable state. But when you are applying electric field, then electrons will be reoriented themselves such that the effect of this electric field will be manifested. Okay, so this due to this reorientation, there will be a transient dipole will be created, and for this is also known as induced dipole. Okay, as you are increasing this E, that is the electric field strength, then your induced dipole moment will change. Okay, and then it was shown that this alpha, where I have taught as a polarizability, how this term is related to this displacement of the atom q. Okay, so it was shown that d alpha by dq should not be is equals to 0. That means it will not be equals to 0 if you want any kind of Raman scattering experiment, Raman scattering phenomena. You want to observe some Raman scattering phenomena, your d alpha by dq is not equals to 0. Okay. In Raman, and also it was talked that we have talked that when you are exciting some sample with some light, the most intense peak comes, which is known as Rayleigh scattering, which has the same intensity as the incident light. Okay, and along with this Rayleigh, there is some lines which will be below this, and some lines which will be above this. Okay, the intensities will be different for two different lines. One is the high intense line is called Stokes line. Okay, and the lower intensity line is called anti-Stokes line. Okay, and this Rayleigh line, Stokes line, and anti-Stokes scattering in the light of time dependent perturbation theory, it was also discussed, and it was shown that just unlike the other spectroscopic techniques which uses an excited state, but in case of Raman spectroscopy there is no excited state. This is called virtual state. Okay.
Sir,
Yes.
Stoke lines will have high intensity, right?
Sorry.
Stoke lines will have high intensity, na?
Exactly. Stokes lines will have higher intensity. Yes.
Okay.
Why this will have higher intensity? Why this will have higher intensity? The Stokes line. This is Stokes line, right? This is the incident, right? This is the Stokes. Okay.
Okay, sir.
So one question will be there today, which will be related to this. And what is this? Is this the same Stokes line? No. This is your initial state in this case. This is your final state. Okay. And this is called virtual state. Similarly, here this is your initial state, this is your final state, and this is the virtual state. So this corresponds to Stokes line. Okay. And this
Okay.
corresponds to anti-Stokes line. Now, at room temperature, which will have more population, this state or this state? This lower state will have more
Anti
population or
Stoke
this higher state? Which one? Sorry?
Stoke lines.
No, I am asking that at room temperature, these two states are there. Okay. So how which will have more population, this lower state or this higher state? Statistical
Hmm.
thermodynamics says that room temperature, range temperature, the lower states always are populated. Okay. As you increase the temperature, the more number of molecules go from this
They
lower
will
state to higher state.
excite.
Exactly. Okay. So at room temperature, more number of molecules will be in this state, right? Less number of molecules will be there. I'm not saying that there will be no molecule. There will be some molecule, but the number is very less. So, since Stokes line, the molecules are excited from these states which have higher population. So that's why Stokes line's intensity will be always higher. Understand the concept?
Yes.
And since for anti-Stokes line, the transition is happening from the higher state, which is less populated at room temperature. So anti-Stokes line will have low intensity. Okay.
Yes.
Yeah. Okay. Fine. So then the difference between the probability of transition for other spectroscopic transition and Raman in terms of transition moment integral, it was shown. It was shown for any spectroscopic transition. We have written that the transition moment integral like this. Okay, but in case of for and also the probability, if you are going for probability, this mod square will be there. Okay, but for Raman transition, since you have seen the virtual state involved, so it will be also in the expression. So how will be that? It will be your final state mu virtual state, then virtual state mu initial state. This whole term will be square. So these two different things are there. Okay. So in the earlier stages of spectroscopy, when you are doing with rotational or vibrational spectroscopy, you are just writing this total transition probability as transition moment integral square. But here two terms are involved because in case of Raman spectroscopy, you also need to consider this virtual state. Then we have calculated the energy difference between two successive rotational Raman levels. Okay, the energy difference were given, and also the determination of bond length was done for homonuclear diatomic molecule, which was otherwise very much impossible for IR spectroscopy. Why? Because, sorry, rotational spectroscopy, microwave rotational spectroscopy. Why for rotational spectroscopy? Because it was difficult. Because in case of rotational spectroscopy, what I have said, your molecule need to have a permanent dipole moment. For homonuclear diatomic molecule, this condition is not satisfied because it will not have any dipole moment. But in case of Raman, which is not dealing with this change in the dipole, which is not dealing with the dipole moment, which is only interested in the change of the polarizability, then for this case, in you, it will show the some spectra or rotational Raman spectra will be observed for homonuclear diatomic molecule. From that, if you can calculate B, then you will be able to calculate what is the bond length. Okay. Then the dependence of the intensity of rotational Raman spectral line on nucleus spin for centrosymmetric molecule, it was also discussed, which will be always which will be discussed today also. And then the symmetry of nucleus spin wave function based of fermion and boson, this was also shown. Then for the case of boson, what should be the nucleus spin, and for the case of fermion, what should be the nucleus spin? Yeah. Okay, so it was shown that for fermion, the nucleus spin will be half integral, like I will be like half 3 by 2, 5 by 2 like that. And for boson, this type of particle, the integral, the nucleus spin will be always integral 1, 2, 3, etc. Okay. So for different kinds of particle, uh, which for fermion, what kind of spin will be there, and for boson, what kind of spin will be there, this was also discussed in the previous discussion. Okay. And then there was a calculation on the number of symmetric and antisymmetric states in terms of nucleus spin. There was some formulas was there. And also it was shown that for 16 oxygen, which has I equals to 0, for this, why the rotational line corresponds to J equals to 0 to 6, etc. was not observed. And the successive levels, gap between the successive level increases. Okay. Yeah. So for this one, I was 0. Okay. For that case, it was shown that the lines correspond to J equal to 0, 2, 4, 6, etc. These lines are missing. Okay, because where it was shown that to, for matching the symmetry from the symmetric algorithm, it was shown that these lines will not appear. Okay, because they does not match the symmetry. And why it is not appearing, I have shown you in the previous class that all the lines, the middle lines are not there. So with the gaps which would be 4b, if all transitions are happening, the gap will become 8b. Okay. And then there was the change in the electron density due to electric field, which was discussed just in the concept of polarization. With the same equation, mu induced is equals to alpha into E. Then the dependence of this applied electric field on induced dipole moment in terms of polarizability, what I have showed you in terms of writing it in terms of matrix, it was shown, and there was concept of polarizability ellipsoid. Okay, and from there we have stopped the discussion. Now we are going to discuss about this to this week's content, which will be starting from polarizability ellipsoid. So mainly our discussion today is mainly focused on vibrational Raman spectroscopy. So in the lecture 42, Professor Sanbakshi has explained the shapes of this polarizability ellipsoid for different types of molecules, like a spherical top molecule, symmetric top molecule. What will be the shape of this polarizability ellipsoid? Okay, and it was shown that for like water molecule, which is completely asymmetric molecule, asymmetric top. I have discussed that in the rotational spectroscopy content. Okay, so water is known as a asymmetric top molecule. So since it is asymmetric top, so moment of inertia are different in different axes. So the shape of this polarizability ellipsoid will be different for different axes. But for case of suppose symmetric top molecule or any kind of linear molecule, the polarizability ellipsoid will be directed towards the main axis. Okay, so for linear molecule or symmetric top kind of molecule, this polarizability ellipsoid will have the same shape. Okay, but for spherical top molecule, which is always identical from each side or each angle, this will have a spherical shape. Okay, so what should be the shape of this polarizability ellipsoid, upon which we have concluded that which will be showing the Raman spectrum. And it was shown that water, all vibrational modes are Raman active. Okay, for water, all the vibrational modes that are present, they all are Raman active modes, because all of them have d alpha by dq is not equal to 0, which is the condition for Raman activity. But in case of CO2, it was observed that the IR active modes are actually Raman inactive. Okay, and vice versa. What is shown that? So CO2 is a linear molecule, right? So from CO2, three different vibrational modes are there. One is symmetric stretch. I'm writing it like this. One is asymmetric stretch. Another is bending. Okay. So when we have examined about this rotational activity or microwave rotational activity, we have seen this the symmetric structure. This dipole moment is not changed. Okay. Just a minute. Yeah. Yes. So for carbon dioxide, we have shown that the symmetric stretching modes are IR inactive. Okay. This is IR inactive. This is IR active. This is IR active. It was also shown. Because whenever there is symmetric stretching, these two CO bond will be stretched by equal amount corresponding to each other. Okay, so they will cancel each other. But whenever if you have seen this lecture, there was the discussion that how alpha is changing with Q, and it was shown that this symmetric stretching mode will show Raman activity, but these two modes will not show Raman activity. So it was concluded that for CO2, which is a completely centrosymmetric molecule, because due to this structure, this one is a completely centrosymmetric molecule, these IR active modes will be actually Raman inactive mode. Okay, if for a centrosymmetric molecule you find some mode which is IR active but Raman inactive, then you can consider that molecule is centrosymmetric. This is very much effective if you want to get some idea about the structure of a molecule. Suppose in this case I have given the example of NO2. If you have to find whether NNO is there or NON is there, okay. So NO2, that is one nitrogen and two oxygen. So are they like this or are they like this? So if you see that if the IR active mode of NO2 is same as IR active Raman active modes, the modes of NO2, if some mode, vibrational mode of NO2 is IR active but Raman inactive, and also the vice versa is possible that some mode which is IR inactive but this is becoming Raman active, then you can consider that in this molecule there should be some center of symmetry. So if the structure is like this, there will be center of symmetry. But if there is this structure there, there will be no center of symmetry. So if by looking at the modes which are, if all the modes which are IR active, if they are Raman active or not, you can strictly say that whether this molecule has a center of symmetry or not. Okay. Next, in the next lecture, there was a discussion on main vibrational Raman spectroscopy. It was shown that the selection rule and energy level for vibrational Raman transitions, they are just same as IR. Okay, there is not much change. And also the selection rule, which was like delta J is equals to 0, plus minus 1, plus minus 2, etc. This is also true for this one also. Okay, for Raman transition, this is also true. That is the selection rule for vibrational transition, for normal IR vibrational transition, and vibrational Raman transition, they both are same. And then it was shown that the Stokes and anti-Stokes lines are just mirror images to each other. Whatever I have said, their intensity will be different, but the positions will be equal. Okay. So if from Rayleigh Raman is 30 centimeter inverse shifted, Stokes Raman is 30 centimeter inverse shifted, then anti-Stokes Raman will be 30 centimeter inverse shifted, but in the opposite direction. Okay. Then there is a selection rule for rotovibrational transition, which shows that delta V should be is equals to 0, 1, plus minus 1, plus minus 2, plus minus 3, etc. And also delta J, it was shown for Raman that delta J is plus minus 2. Okay. These two conditions will be followed for a selected rotovibrational transition. And depending on that, delta J is equals to plus minus 2, this S branch and O branch lines are observed, because this S branch line corresponds to delta J is equals to plus 2, and this O branch line corresponds to delta J is equals to minus 2, and this Q branch line corresponds to delta J equal to 0. Okay, and using this energy and adding it or subtracting with the incident light energy, one can get easily where should be the Stokes and anti-Stokes Raman lines will be positioned. Okay, and in the next lecture, there was some discussion about plane polarized light. Okay, what is plane polarized light? A normal light is actually isotropic. Okay, so it will be isotropic in any direction. But if I want that my light or my electric field or magnetic field of light should be positioned in a particular direction, then I need to use some nickel prism. Okay, and from this nickel prism, you can create a particular directional line. Okay, and from that you can measure this degree of polarization, which is measured as I perpendicular and I parallel. What is I perpendicular? You need to understand. Suppose my light is passing through this, so this polarizer is like this. Okay, so it is only allowing light which is parallel to the plane. Suppose you see my hand. Okay, so there is some light is coming like this. Okay, so this is positioned like this. This is positioned in this direction. So this is what is I parallel. I parallel will be, that is some opening which will be, suppose okay, so my light is passing, this have all the directions. So this is my nickel prism. After passing this, my light, I am only getting this light. Okay, I am blocking all other directional lights. I am only taking this light which is like this, which is moving like this. Fine. Now I have to calculate when I want to get I perpendicular. and I parallel. First, for I parallel, I need the same slate. I am measuring where these two pass to there. Okay, and also I perpendicular will be this one. Okay, so how much light is passing through this? This will be dependent on this degree of polarization, and this will have 0 or 1 value. Okay, so unpolarized light, for unpolarized light which is not polarized in a particular direction, I perpendicular and I parallel is same. Okay, so for unpolarized light, this rho equals to 1. So for unpolarized light, this rho will be equals to 1. But it could also have 0. When it will be 0? If it is completely polarized towards the parallel, that is I perpendicular is 0, then your degree of polarization should be 0. So this range is actually between 0 to 1. So it is a fractional value. Okay, minimum value is 0, maximum value is 1. And it is said that this is a statement just if rho is greater than 0.75, then Raman lines are actually polarized. And if it is less than 7.75, then I can say that the Raman lines are actually depolarized. So next in the discussion of resonance spectroscopy. So what is the resonance spectroscopy? Earlier cases when we have talked about some different spectroscopic techniques, we have utilized the electric field of the light. So we have dealt with the electric field of light. But you have forgot that also there is some magnetic field. Okay, there is some magnetic field associated with this light. Okay, and when this magnetic field actually interact with matter, what is the change is that is possible? It is actually measured in the resonance spectroscopy. Okay, and actually it was shown that this magnetic field actually hampered the nuclear spin. Okay, so it was shown that how it is related with the spin angular momentum, the speed of the magnetic field in terms of B. It was shown of this expression. So the spin magnetic moment was written like this. This is called gyromagnetic ratio. This is E by 2me, and this is called S. Okay, so S is nothing but S is given by H cross root over, this is the spin S on S plus 1. And also this was modified in terms of Bohr magneton and gyromagnetic ratio gamma, that your G0 beta will be gamma H. Okay, this was also shown that this is called Bohr magneton, this is have some formula, and this is called gyromagnetic ratio. Okay, and then the how the relation that as I am showing, this was proved, and also it was shown that for under any magnetic field your z component of J is constant. Okay, but it was shown that if that means because this J, why the J is important, because J is actually interacting with the magnetic field B. Okay, so your J, that means the angular momentum of this nucleus, when I am putting some magnetic field in some direction, it will interact. Okay, so magnetic field will have only one direction. Suppose you are giving the magnetic field in the z direction, so the only Bz component will be there, but your angular momentum will have three components: Jz, Jx, Jy. Okay, and it was shown that the Jz is constant, but Jx and Jy are changes. And but whenever they have calculated this Jx square by Jy square, they have shown that this is constant, which ultimately tells J square, which is nothing but the summation of all this, is constant. J square is nothing but J x square, Jy square, but Jj square is constant. So Jy and Jx are not constant, but whenever you are taking this J square and Jz, this is constant. Okay, and then the expression of Jx and Jy in terms of trigonometric functions, they were given in terms of trigonometric function how they looks like. It was shown that if Jx you can take as a cos omega t, and then and jy you have to take in terms of a sin omega t, such that if you are they are squared up and then added up, you will get only one. Okay. So in terms of trigonometry function, you can find this omega, which was found. Because how can you find that? You can find that if you know this relation, that if you are taking double derivative of say x with respect to t, it will give you that this relation omega square will be equals to gamma into b. Okay. So this frequency, this j, then become precise along the surface of a cone, and which will have angular velocity which is given by omega, and this is called Larmor precision. Okay, Larmor precision and Larmor frequency. Okay, so there was a discussion on the Larmor precision and also Larmor frequency, and then it was shown that for s equal to half, two spin states could be there. Okay, one could be ms equals to plus half, another could be ms equals to minus half. So they are designated as if s equals to half, ms equal to plus half, we will call it alpha state. If s equals to half and ms equals to minus half, we will call it beta state. And then nuclear spin, in terms of number of neutron and proton, it was shown that if both are odd, this proton number and neutron number both are even, then this nuclear spin will be zero. Okay, so it was shown that proton neutron spin. So if this is even, then the spin will be zero. If this is even or this is odd, and if this is odd or this is even, so this is zero. Okay, don't confuse it with odd O. Okay, and then another scenario could be these both are O or dot. Okay, so if in the middle case, that is if there is this, in this case, that is proton is even and electron is odd. In this case, in these both cases, you will see half integral spins. Okay, half 3/2, etc. And in this case, when they are both are odd, you will see integral spin. Okay, 1, 2, 3, like that. Okay, so nuclear spin is denoted here as I. So whenever I will tell you about that I of any molecule. Okay, so you first remember that whether there is number of protons even or not, or whether is number of neutrons even or not, then you can say that yes, this molecule will have integral spin, zero spin, or half integral spin. Okay, so the molecules which will have I half I is equals to half 3/2, which kind of particles are there? The molecules which have uh, 1 to 3 kind of spin, they are resembles what? They are actually fermion like thing. Okay, but I have said this earlier, and they are like boson. Okay, next it is shown. So the splitting of these levels is depends upon magnetic field. Okay, so splitting of these electronic levels, splitting of these levels using magnetic field is known as Zeeman effect, and these levels are known as Zeeman level. Okay, so this is possible for both electron and nucleus. Based on this electron and nucleus, where should be these positions, how they are separated, what should be the difference, which states will be in the higher energy. Using that concept, two different spectroscopic techniques were there. One is called nuclear magnetic resonance spectroscopy, which is you must know about NMR spectroscopy. Another is electronic spin resonance spectroscopy, which is also known as ESR spectroscopy. So these techniques were developed using this concept. Okay, that how the nuclear spin states are distributed among themselves and how the electronic spin states are distributed among themselves. What should be the energy gap? What should be the different things? Okay, so very much questions are there about this nuclear NMR and ESR spectroscopy discovery. So I will going to solve that. I will be going to solve that. Before that, there is someone who, yeah. So the same here. What I have asked about Gmail level. So there is another level, the splitting of the rotational levels I have shown you. how the rotational levels are splitted, and due to this electric field. Okay, a similar effect using electrical field light. Okay, so what is this called? You understand my question? Just a simple question. Your energy levels are separate, are in the degeneracy level. You are giving magnetic field, the energy levels are split. Okay. Similar effect I have shown, but for rotational case, that much hint I am giving you. For rotational case, these levels are there. Whenever I am applying electric field, the levels are splitting. Okay. Here, this is called Zeeman effect. Okay. And the similar effect was observed, but there was instead of magnetic field, there was electric field. And so, what was the name of this effect? You can remember.
No, sir.
Have you heard about Stark effect?
Yes.
Yes.
It was there in the previous
Yes.
lectures.
And whenever I have discussed the Stark effect, I've told you that the same effect which is known as Zeeman effect. A question I can remember that some question was there.
Magnetic
There was some
field.
option of Zeeman effect. I told you that whenever there will be magnetic field,
Yes.
it will be split, right? Now you are seeing this Zeeman effect.
Yes.
Okay, fine. Okay, fine. Okay, so I'm moving to questions. Uh, this is my first question. That Raman scattering intensity is proportional to lambda to the power minus 4. So which of the following incident light will produce the maximum scattering intensity? Okay. So red, blue, or yellow, or green. So what could be the answer? So what I'm saying that Raman scattering intensity will be proportional to 1 by lambda to the 4. So what does it tells you? That for a light which has low lambda, this will have higher scattering intensity, right? So low lambda implies higher scattering intensity, right? I can write that. So we have shown that it is told that Raman scattering intensity is proportional to 1 by lambda to the power 4. That means if you are increase lambda, then your light will be much more intense. Okay, if for low lambda, this light will be much more intense. Now you can tell me which will have low lambda. So the question is which of the following will produce maximum scattering intensity? Yeah. So maximum scattering intensity will be produced in which case? So as you can see from this relation, if to be this maximum, this lambda should be minimum. Okay, because it is inversely proportional. So to get this intensity maximum, your lambda should be minimum. So you have to find among these red, blue, yellow, or green which will have low lambda. This will be your answer. So can you guess which will be have low lambda?
Blue.
Blue, exactly, exactly. And this since blue, we have said right that blue have low lambda. We see there is some significance of this low lambda. You know, Some physical property is related to this, some physical phenomena you have observed, whose actual reason is this one. Do you know?
No.
Okay. So what is the color of the sky?
Raman spectra. Raman
Yeah?
effect.
Color of the sky.
The blue.
Blue. Why blue? Because blue has low lambda and hence the scattering intensity will be maximum. So you will see
Yes,
this
that's right.
that color mostly. Okay. So you see this blue color most. So you find this answer in also lecture number 37, that for Raman scattering intensity, since it is inversely proportional to lambda to the power 4, hence the lowest lambda always will have higher scattering intensity. Okay. So among the 7 colors of the visible spectrum, blue will have lower lambda. The lambda of the blue will reside like in 450 to 460 70 region nanometer. Okay. And your green will reside next is green. So if you know this Bezier thing, VIBGYOR, so as you are going from left to right, your lambda increases. Okay. So your red will have highest lambda, and your violet or blue, this kind of things will have low lambda. Okay. So the answer is blue. Okay. Next question is, CO2 has 3 kinds of normal mode: more symmetric, asymmetric, bending. Okay. This should be written as, I don't know, this should be written as symmetric stage, asymmetric stage, and bending. So your question is, which of the following is true for them? And options you can see here that they are asking about the IR and Raman activity of these modes. Okay, so you have to find which modes will be Raman active and which modes will be IR active. So what should be the answer?
Symmetric mode is IR active.
Which option? Fourth one? Fourth one or third one?
Yes, fourth one.
Fourth one. Okay, fine. Okay, so first of all, you need to know what is CO2. Whenever this kinds of question comes, that Raman activity and IR activity, you first see what is the structure of the molecule. First focus on that. What should be the structure of the molecule? You see, this is CO2, and you know there is some center of symmetry. Okay, since there will be some center of symmetry in CO2, so it will always follow the rule of mutual exclusion. Okay, what is the rule of mutual exclusion? It says where the modes which are IR active, this will be Raman active. Okay, so this is your first idea. Before moving forward to which modes are IR active and which modes are Raman active, this is your basic first idea, that CO2 is a completely linear molecule and also it possesses some center of symmetry. Okay, so since it possesses a centrosymmetric molecule, this will follow always mutual exclusion principle. Okay, what is the mutual exclusion principle? That its IR active modes will be Raman inactive and vice versa. So IR inactive modes will be Raman active. Now you have to consider that you can see here that two options are getting cancelled, right? Because it is saying that both IR and Raman active, two options, right? But it is not possible. If some mode is Raman active, then it must be IR inactive. If some mode is IR active, then must be Raman inactive. But here it is saying both IR and Raman active. This is not possible. So these two options I am just cancelling. Okay. Now my main photo is coming, that I have to find this among this symmetric mode and asymmetric mode, which is IR active. So you can find this answer in also lecture number 42, and I'm also doing that. CO2. So three different modes could be there. Suppose this oxygen, the oxygen. So they are symmetrically stretched equal amount but in the different direction. Okay. So three different modes I am drawing. What is the first mode? You can see that in this from the water picture you can see this is symmetrically stretched. Okay, these two arrows are similar. Symmetric stretching mode. What is this mode? This is called the amount of stretching is different for this mode asymmetric stretching. Exactly. So this is called asymmetric stretching mode. So the spelling is wrong. Asymmetric stretching mode. This last one is not symmetric nor asymmetric. This is just bending mode. Okay. So you have to check this IR and Raman activity. So if you can check IR activity, you can definitely tell Raman activity. Okay, because you know it will follow mutual exclusion principle. Okay, so if it shows any mode is showing IR activity, this will be Raman inactive, right? So for you symmetric stage for IR for IR activity, your condition is d mu by dx will be not equals to 0. Okay. So this was your actual condition that for IR activity your d mu by dx will be always not equals to 0. So that means your dipole moment will not change. Okay. So in that case you can see the symmetric stretching mode here dipole moment is not changing. So it will be Raman active. Okay. And here in these two cases the dipole moment is significantly changing. So this will be Raman inactive. Sorry, IR inactive. Right. So you know what I have said, if symmetric staging mode is IR active, then this Raman will be okay. So sorry, just a minute. Right. This mode is actually what I've did wrong. I've saved that actually. Just a minute. Yeah. So your d mu by dx, that is the change of the dipole moment will be non-zero. That means your dipole moment need to be changed. Okay. So sorry, I have told you wrong. So your dipole moment needs to be changed. So since in this mode dipole moment is not changing, so I am just cancelling this part. So here I am writing this IR activity. This is Raman activity. So in this case, the dipole moment is not changing. Okay, so it will be Raman inactive. But in these two cases, this will be in these two cases dipole moment is getting changed. So in those two cases will be IR active. Okay, and that's why in CO2 in CO2 in case of CO2 in IR spectrum you just see two bands. Okay, And in the Raman case, you know, if this is IR inactive, this mode, this must be Raman active. Okay. And if this is 2 are Raman active, then this 2B must be Raman inactive. Right. So you can see here that for symmetric stretching mode, IR activity is not there, but Raman activity will be. Similarly, for asymmetric stretching mode, it will be IR active but Raman inactive. Now you have to see the two options that are given. So the symmetric mode is IR active but Raman inactive. Okay, you can see here the symmetric mode. Is this the true thing? No, because the symmetric mode is IR inactive. So here it is IR active. So only answer is possible is this one. Asymmetric mode is IR active, yes, but Raman inactive. Okay, this you can cancel. This is Raman inactive. Understand?
Yes.
Okay. So just for a small query, in it was shown that yeah. So for CO2, it was shown that in IR spectrum, two bands appear, right? It is observed. But if you go through this 3n minus 5 or 6 rule, since CO2 is a carbon triatomic molecule, so it will have 9, how much degrees of freedom? 9, 3 into n, 3 into 3, 9, 3 are translation, 2 are rotation. So number of vibrational modes is 4.
4.
But in CO2, in IR spectra, you are seeing only 2 bands. Why?
2 bands.
For 4 different vibrational, you are expected to see 4 vibrations, right? So why are you seeing 2 bands? You understand my question?
Yes.
Yes. Because for CO2, you are getting 4 vibrational bands. Okay, so there will be 4 different modes of vibration. So for different vibration, you are expected to get IR spectra different positions, but for CO2, we are getting only 2 bands. Okay, so for 4, there is coming 2 band. Why? Okay, so for 4 different modes, actually, one is symmetric stretching, another is an asymmetric stretching, and there will be 2 bending modes. Okay, these are the 4 modes that are possible for CO2. One symmetric stretch, another asymmetric stretch, and 2 bending modes, right? But it is shown that for CO2, which is inclined in a particular plane, its 2 bending modes come of equal energy. Okay, so these 2 bending modes will have equal energy, so they will behave like just one mode. Okay, in IR spectra, these 2 modes will be overlapped. Okay, suppose one for one bending, this is coming here. For the other bending, this is coming to the same thing. So you are getting the same spectra, same position. So this will behave as a single mode, right? So
Yes.
and from asymmetric stretching, you will also get one mode. But do you will get any mode from this symmetric stretch?
No.
Why? Why
It
you
is
not get?
iron inactive.
Exactly, because it is IR inactive. So how many bands you get?
2 bands.
Exactly. That's why in case of carbon dioxide, when you are taking this IR spectrum, you will see only 2 bands appear. Okay, got it?
Yes.
Yes. Okay, so moving to the third question. Had at room temperature, anti-Stokes lines are very weak. That the question you have asked me, right? For the Stokes and anti-Stokes, which will have very weak intensity. So now you will be able to answer this. Which will be the answer?
Very few molecules are in V is equals to one state.
Exactly. This is the answer. So you can find this in also lecture number 38, that what I have said you, that this anti-Stokes lines occurs due to transition from equal to one state, which is late populated at room temperature. So I'm again drawing this. So I'm again drawing that. So for Stokes line, this is my initial state, this is my final state. So I'm exciting the heat here. So is this the excited state? What is this state? Just like other spectroscopic techniques, it is the excited state. Yes, yes.
Virtual state. The upper one.
Virtual state, exactly. This is nothing but virtual state. So here this is I and this is F. Okay. So which one is Stokes line? Which was in anti-Stokes line? Tell me. Which one is Stokes line? Which was in anti-Stokes line?
The first one is
Means left one.
Stokes line.
Left one.
Yes.
Left one is Stokes or anti-Stokes? Confused?
Anti-Stokes. No?
Confused?
Yes. Left
Yes.
one are anti-Stokes and right one are Stokes lines.
Sorry.
Left one are anti-Stokes, right one are Stokes lines.
Yes. I'm drawing fast. That doesn't mean that this is the Stokes line. This is the anti-Stokes lines. Okay. And this is the Stokes line. Why? Because here the transition is happening from this state, excited state. Okay. And in this case, the transition is happening from the ground state. And what I've said that for anti-Stokes line, intensity are very weak. Why? Because in room temperature, at room temperature, the excited state is very less popular, very less number of molecules in the excited state. So its intensity will be very weak. Whatever you have said, it's correct. That very few molecules are in the P equals to 1 state. Okay. Got it?
Yes.
Okay. So you have seen this diagram for Stokes and anti-Stokes, and another line was there, right? What was this called?
That's the
Another line was there other than the Stokes and anti-Stokes.
Rayleigh.
Really, no, this is called Rayleigh line. Okay. Yeah. So this is the this is the incident light. This is the emitted light. Okay. This is called Rayleigh. Okay. So three different kinds of transitions are there. Fine.
Yes.
Next question. So which of the following statement is true? Stokes line are higher in frequency than the anti-Stokes line. The anti-Stokes lines are higher in frequency than the Stokes line. Rayleigh lines are in higher frequency than the Stokes line. Rayleigh lines are in higher frequency than the anti-Stokes line. So you are asked that where should be your Rayleigh Stokes and anti-Stokes lines will be there. Okay. So whenever you are getting spectrum, if you see any Raman spectrum, most intense line will be this one. Okay. And this side there will be something. This side there will be something. In the equal distance with the different intensity there will be something. Okay. So what is this line?
Rayleigh.
Rayleigh. Yeah. This is Rayleigh. Now you have to tell me if nu bar If I am writing new bar, okay, or new, okay, new bar is too much confusing for you. So I am writing if new, if increasing in this side, so you have to tell me if this is anti-Stokes or Stokes.
Anti-stroke.
Just seeing the intensity?
Yes.
No, but I have drawn intensity
Equal.
arbitrarily. Yeah, it could be increase or decrease, but just to show peaks positions, I am showing. Okay, so if this much is equal. Okay, they have to tell me that at higher frequency which transition will be there, which lines will be there. It will be Stokes or anti-Stokes. So if you can find this answer in lecture number 38, that Stokes lines occurs at a lower frequency than the Rayleigh line. Okay, so you have measured it correctly that it will be anti-Stokes line and this will be Stokes line. Okay, so you can see that also if I am drawing the diagram once again. Yeah, I think I am drawing this Stokes line nu I will be nu s. Okay, so you can see is this nu s is higher or lower than nu I?
New I.
Which one is higher, nu I or nu s?
New
Nu
I.
nu I. Don't confuse. You can see this diagram. Okay, so nu I is this to this, and nu s is this to this. You can see which one is lower, right?
Yes.
Yes. So for Stokes case, this nu y is greater than nu s, or inversely I can write this opposite side that nu s will be less than nu y. So uh, the frequency of the Stokes line will be lower than that of incident light or that of, and since you know these Rayleigh lines are just coming at the incident light position, so your Stokes line will be around in the left side of this Rayleigh line. Okay, that's why since they are in the lower frequency side, so in the Stokes line you can see it will have lower frequency, right? And this is the another diagram. So here this is the initial state, this is the final state, this is the virtual state. Okay, so I am exciting this from there and that. So now in this case we will be same or are different. Nu I and nu s, which will be higher?
New I.
Nu s will be higher, exactly. So nu I will be less than nu s. So in other term, I can write your nu s will be higher, it will be low, sorry, your nu s will be higher than nu I, right? So your the anti-Stokes line, this is the anti-Stokes, right? This is
Yes.
the anti-Stokes line. So you can see this nu s for anti-Stokes line will be higher than the incident light. And also the same thing we have used in the previous case that this incident light is nothing but the Rayleigh line, right? So your anti-Stokes line will have frequency which will be higher than this Rayleigh line. So if this is a Raman spectrum, okay, so if this is a Raman spectrum, in the lower and lower frequency side there will be Stokes line, in the higher frequency side there will be anti-Stokes line. Okay, now you have to find which options are correct or is correct. First of all, Stokes lines are in a higher frequency than the anti-Stokes line. Is this correct? Is saying Stokes lines are in higher frequency than anti-Stokes. Is this correct?
Yes.
Yes. Which one has higher frequency? Stokes or anti-Stokes?
Stokes.
The diagram is drawn here. See. Okay. So for your clarity, I'm just asking this one. Okay. So these lines are for Stokes or anti-Stokes. These are Stokes lines. These are anti-Stokes lines, right? And this is the frequency scale. So as you go from left to right, your frequency is increasing, right? So as you are going from left to right, your frequency are increasing. So which one among these three lines, which will have higher intensity or higher frequency?
Stoke lines.
No, you are again making mistake. Stokes are at lower frequency. You can see.
It will increase. Yes.
Yes, we also have derived that. There are new ways. That is, the frequency of Stokes will be less than that of incident. So higher will be anti-Stokes line. That will be higher in frequency. Then there will be relay line, and so the lower will be Stokes line. Right? So your first option is saying the Stokes lines are higher and a higher frequency than anti-Stokes line. This is true?
No, false.
No. Next one is anti-Stokes lines are higher in frequency than the Stokes line. Is this true?
True.
Yes, this is true. Anti-Stokes lines are higher in frequency. Rayleigh lines are in higher frequency than Stokes line. Is this true?
True.
Hmm?
True.
You can see the diagram on the right side. This is
Really.
Stokes, this is Rayleigh, this is anti-Stokes. As you are going from left to right, your nu is increasing or frequency is increasing. So which one have higher frequency, Stokes or Rayleigh?
Really.
Rayleigh, exactly. So your Rayleigh lines will have higher frequency than the Stokes line. So if this is correct.
Yes.
Now Rayleigh lines are in higher frequency than anti-Stokes lines. So among Rayleigh and anti-Stokes, which will have higher frequency?
Anti-Stokes.
Anti-Stokes for Rayleigh lines must be in lower frequency. So it will not be correct. So your correct answers are two answers. One is anti-Stokes lines are in higher frequency than the Stokes line, and Rayleigh lines are in higher frequency than the Stokes line. Okay, you got it?
Yes.
We are still confused about this frequency distribution of the Stokes, Rayleigh, and anti-Stokes. Is this clear?
Yes.
Okay, so moving to the next question. So in vibrational rotational Raman spectroscopy, delta J is equals to plus 2 corresponds to which transition? P branch, Q branch, O branch, S branch.
S branch.
S branch.
Yes.
Okay. So you got this is a straightforward question that in vibrational Raman spectroscopy, this delta J is equal to plus 2 corresponds to which transition? This is going to find in lecture number 43 that the selection rule corresponding to delta J is equals to plus 2, which gives to S branch. Exactly, you are right. And delta J is equals to minus 2, which will be that?
O branch.
O branch. Then what about P and R branch? This is S branch, right? And another branch is left. Why it should be left? Including that
Two branches. Delta J equal to 0.
0. P and R.
Minus 1.
Which one is minus 1? P is minus 1 or plus 1?
P P is plus 1, R is minus 1.
P is plus 1.
Yes,
Sure?
yes.
Yes. This will be minus 1. P is minus 1. R will be plus 1. Okay. So in Raman, vibrational Raman spectroscopy, these 5 branches are present. Okay. Is these 5 branches you can see? No. You are see only 3 branch. One is S, one is O, another is Q. So why you cannot see this P and R branch in rotational Raman, vibrational Raman spectroscopy? There 5 branches are there, right? So in Raman spectroscopy, you see this O branch and S branch. Okay. So you don't see any kind of uh, P branch or R branch. Why? Why you don't see? So what is the selection rule for rotational Raman transition?
Got it. Because the selection rule for Raman transition is delta J should be plus or minus 2. That's
Minus
why.
2, right?
Yes,
So in this case, there will be no selection rule corresponds to delta J is equals to plus minus 1, right? So in that case, you will not observe any P or R branch. You will see a Q branch, the middle, and then from 6B distance, you will see in the left side you will see O branch, and the right side you will see S branch, right? So
yes.
your answer is S branch. Okay. So yeah, I'm just coming just in 1 or 2 minutes. Okay, just coming. Okay, so sorry for the delay. Okay. So we are done for this question. So I'm moving to the next question. So the question is the molecule active in rotational microwave, rotational Raman and IR is which of these following? Okay. So which would be the answer? Which will be active in all these three cases? Hello? Hello?
Four.
Yeah. So what should be the answer?
CCl4.
CCl4. So here you are asked to find some molecule which will show these three different kind of spectra, right? So CCl4, Br2O2, in these three types of thing, one thing is common. You can find it. Can you find it? Think. There is a similarity between CCl4, Br2 and O2.
They will show symmetric stretching.
Uh, Not that much. Very basic understanding from the structural point of view. Are the three structures correct? This will be for each pair. Are the structures are correct? Yes. Okay. So all CCl moments will be in this direction. All then these other CCl movement will be in this direction. So these three have one thing in common. Have you found out that?
They are linear molecules.
No, CCl4 is not linear.
No, no, the other three.
No, I'm not. I'm just yes, okay. So put this aside. We're not looking at that. Just these three things. This CCl4, Br2, and O2. What is the thing that is common? If you find that, then you will get the answer. Just one missing link. Did you find out? What should be the mu? Dipole moment for CCl4? 0. Because the CCl, all the moments will give a resultant moment in this direction, which will be cancelled by this CCl moment. So it will have 0 dipole moment. Now for Br2, what should be the dipole moment?
Zero. It will also cancel each other. No?
Sorry?
It will also cancel each other.
No, for Br2 it will not cancel. See, the two things are different, okay? One is presence of dipole, another is the cancellation of the dipole. Okay. Suppose you are creating something and this is cancelled by someone the same equal magnitude, and then you are getting zero. This is something, and you are not getting something. Also, this is zero. This is another thing. Okay. So Br2 is a homonuclear diatomic molecule, right? Homonuclear diatomic molecule means the two bonds will be shared between two Br atom. So there will be no dipole. So since no dipole, so no dipole moment. Similarly, for oxygen, which has two oxygen molecule, oxygen atoms, the same atom is there, so its mu will also be zero. So this is the missing link that I was talking about. Got it? That these three molecules will have a zero dipole moment. These three will have zero dipole moment. What will be this zero dipole moment will be possible for HBr?
No.
No, because the two atoms are different. Okay? So which one will be have higher electronegativity? They will pull the electron density. Okay, so a dipole will be created. So it will be non-zero. Okay. Now you know that zero dipole moment of a molecule. That means this one of these three modes will be inactive. One of these three will be inactive. Which one will be inactive for zero dipole moment molecule?
IR inactive.
No. Iron inactive condition is, don't get confused among them. Iron inactive condition is d mu by dx should be non-zero, right? That means your mu should change. That doesn't mean you need to have some mu initially, right? They are saying that your mu should change. Suppose from it was initially zero, from that you are getting one. So this is change, right? So it will show vibrational spectrum or IR active, right? And also for rotational Raman activity, your d alpha by dx should be non-zero, right? In that case, only you can see this rotational Raman activity. But one thing is very necessary for microwave Raman. Whenever I was discussing about microwave Raman, microwave rotational spectroscopy, I was telling that molecule main condition is molecule should have a permanent dipole moment.
Yes.
Yes. So if the dipole moment is zero, so will it show this microwave rotational spectra?
No. No.
No. That means these three molecules will be rotationally, microwave rotationally inactive. So only example, only left thing is HBr. So this is the answer I have written here that for rotational microwave activity, molecules should have a permanent dipole moment. For IR activity, there should be a change in dipole moment. Also for rotational Raman activity, there should be a change in polarizability. So the answer is HBr that will be showing all of these three spectra. Got it? Got it?
Yes.
Okay. So this is the next question. Two kinds of resonance spectroscopy has been discussed in the class. One is electron resonance spectroscopy. Another is named proton resonance spectroscopy, which is known as also NMR. So you have to identify the correct statement. So question is that in NMR, alpha state has higher energy than beta state. In NMR, beta state has higher energy than alpha state. In ESR, alpha state has a higher energy than beta state, and also in ESR, beta state has a higher energy than alpha state. So you have to find in NMR, okay, just pictorially I am showing that these are two energy levels. Okay, so suppose this is for ESR, this is for NMR. So you have to find which one level is alpha, which one is beta. So you can see this, if this is the energy axis, you can see that this is a higher energy level. So for ESR, which one have higher energy? For NMR, which one have higher energy? So you have to find that. Can you guess which is the answer? Can you guess? Or should I give some hint? Okay. So I'm giving some hint. Okay. So if you follow this lecture, I'm not deriving the energy expressions for all these. The energy expressions are derived. I'm just writing the values that for electronic case, for electron, it was found that the energy of this alpha state was given as half. This is Gs beta into B. So this beta is not the beta state. This beta is Bohr magneton. Okay, and this energy of this beta state is half. Sorry, minus half Gs beta B. Similarly, for nucleus, E prime. Okay, I'm suppose I am writing E prime. E prime alpha will be half G of nucleus beta of nucleus into B, and E of beta, which is I am writing E of beta prime, so it will be minus half of Gn beta n B. Okay, so you just need to tell me that what is the relation between E alpha and E beta? Which one is higher, E alpha or E beta? You understand my question? Yes. So which one will be higher? So I'm giving you some another hint. This beta, what is this called? I have called it Bohr magneton, right? All these terms are described there in the lecture. Okay, this is called Bohr magneton. Okay, and for new electronic case, it is negative. Okay, so electronic case, this Bohr magneton is negative. So which will have higher energy for this electronic case?
E alpha.
E alpha. Why it will have higher energy?
Bohr magneton is negative for E
Sorry.
beta. Bohr magneton is positive for E alpha, so the value increases.
No. What I'm saying, beta is negative for this electronic case. Okay. For electronic case, this beta is negative. For nucleus case, beta is positive. So you can see that for electronic case, the alpha will be higher in energy. Okay, so your E alpha will have higher energy, and your E beta will have lower energy here, right? But in this case, you can see your E beta will be have higher energy for nuclear case or proton case, okay? And your E alpha will have lower energy here. So, what will be the relation between E alpha and E beta for electronic case? This will be higher in energy, okay? This negative means it will be higher in energy, and the positive means it will be lower in energy, okay? And for this case, what will be the relation? C alpha prime, okay? So I'm designing is that A alpha and B beta prime. It will be E alpha prime will be lower in energy than E beta prime. Got it? So options you can find it in lecture number 46, the reference that for electron or SR, E alpha is greater than E beta, okay? Because Bohr magneton is negative. But for proton case or NMR case, it E alpha is less than E beta because the nuclear Bohr magneton is positive. Beta n is positive here. Okay. So in question, first option is in NMR alpha state has higher energy than beta state. So for NMR, which has state has higher energy, alpha or beta?
Beta.
Beta. And for ESR, which one has higher energy? Alpha. Right? So for NMR, alpha state has higher energy than beta state. Is this true?
No.
NMR beta state has higher energy than the alpha state, right? In
Yes.
ESR, alpha state has higher energy than beta state. This is right. ESR beta state has lower energy than alpha state. This is not possible. So this is the answer. Okay. So NMR beta state has higher energy than alpha state, and ESR alpha state has higher energy than beta state. Got it? So the next question is you have to identify the correct statement. The frequency of NMR is less higher than that of ESR. The frequency of ESR is higher than that of NMR. Both are similar or none of the above. So they are asking
P of NMR is higher than that of ESR.
frequency of NMR is higher than that of ESR. Okay, fine. So this is alpha or beta for ESR. Which is this one? This one is beta, right? For ESR, this is alpha. For NMR, opposite is the thing. Okay, this is the alpha, this is the beta state, right? So if you find for each case the energy expressions I have given you in the previous question. So if you just put it and certain approximation, the delta E for ESR, you will find this delta E for ESR will be large. Okay, and also the delta E for NMR will be low. Okay, so because the delta E, if you find what is delta E is just the energy difference between alpha and beta state. So here there is no concept of this positive or negative sign. Just you can see that the GS values are different, and also the energy difference depends upon this gap value. Okay, and it was shown that for delta E, the ESR is higher than compared to delta E of NMR. So if delta E is higher, that means nu is higher or lower. Delta E is nothing but H nu. So if delta E is higher, that means nu is
Higher.
higher. And if delta E for NMR is low, that means for the nu for NMR will be lower. Okay. So you can find it here in lecture number 46 that the energy difference between two speed states is larger for ESR compound compared to NMR, for which the energy difference between two speed states is small. So your new ESR, will be greater than mu of NMR, right? You can see here that nu is higher for ESR, nu is lower for NMR. So ESR will have higher frequency than NMR.
Mhm.
Understand?
Yes.
Yes. Okay, so next is a straightforward question. What should be the nuclear spin angular momentum of 1602? So I have told you that dep- depending on the number of proton, number of neutron, you can designate the nuclear spin, right? Okay. So whatever I have said you that if both are even, nuclear spin will be, if the molecule contains even number of proton and even number of neutron, what should be its nuclear spin? I have told this in the beginning that three different kinds of nuclear spin could be there. I have three different values. It could be zero, it could be half integer, or it could be integer. Okay. So this is one case, this is another case, this is this case, another case. So in this case, if both are even, what should the nucleus be? This should be zero. Okay. Now another combination is number of proton is even, number of neutron is odd, or number of proton is odd, number of neutron is even. This is another case, and there is another case also that both are odd. So I have told you that in this case, if one is even, another is odd, then in this case you will see a half integer spin, right? Hmm?
Yes.
Yes. And if both are odd, you will see integer spin. And I have told you which kind of particle they will behave like. If half integer spin is there, they will behave like fermion, right? And if integer spin, they will behave like boson, right? So you have to calculate for 1602 if this combination, which of this combination is followed by 1602. Now you can do that. For 1602, number of proton is positive and sorry, number of proton is odd or even. How many number of protons oxygen have?
Eight, but it is two,
Hmm?
six,
How much?
16.
No, 16 is its total neutron plus proton is 16. How much proton is among them? How much electron oxygen have? How many electrons? Oxygen. How many electrons oxygen will have?
8.
8 electron, right? And you have also done this configuration. 1 is to 2 is to, right? So if it has 8 electrons, how many protons will have? It have 8. Very very school level understanding. This is electron number equal to number of proton, and total mass number is 16. Among them 8 is proton. So how much is the neutron? Total mass number is 16. Among the 16 number, 8 is proton. So how much are neutron?
8.
8. So you see in oxygen 16O2, it will have 8 protons and 8 neutrons, right? So it will fall under which category among these three?
First one.
First
Even,
one,
even,
even. How much will be its nuclear spin?
0.
0. Exactly. So that is the answer. So for this oxygen, the answer is 0. You got it? How have you calculated?
Yes.
Yes. Okay. So this is the next question. This is another straightforward question. This was also discussed in the very basic, very starting. that which of the following are constant? J square, Jz, Jx, Jx plus Jy. I have told you. So what is the answer?
Jx plus Jy.
Another is just only this one or anything else are there?
J square, first one.
First one and this one, right?
Last
Last one and first one.
first one and last one.
First one and last one. Okay. So what I have told you, you will find also in lecture number 45 that I have told you this Jz is always constant. Z component is always constant. Okay. But your Jx and Jy will depend upon each other and also on time. Okay. That how much field you are giving with time, they will depend upon that. But I have shown you that if you do jx square and if you do dy square and if you add them up, you will find that they are constant. Okay, all these calculations are done in this lecture, and you will find this jx square plus jy square is constant. So, and you also know this jx square plus jy square is not equals to jx plus jy, right? These two are different. Jx square plus jy square and jx plus jy, these two are different, right? Hmm?
Okay, sir.
Right now? If you write a plus b and you write a plus square plus b square, both are different, right? Yes,
Yes.
yes. So your jz is constant, and another constant term is jx square plus jy square. So if you find j square, which is nothing but jx square plus jy square plus jz square, so your g part is constant and your jg is constant. That means jg square will be always constant. So two constant will add up to give some constant. So you can see which two factors are constant. J square is a constant term and Jz is also a constant term, right?
Yes.
So in an external magnetic field, Jz is constant and also Jx square plus Jy square is constant, that which gives J square total is constant. So if J square is constant, Jz is constant, but Jx is not constant and Jx plus Jy is not constant, but if their squares are given, then they will be constant. You find the answer? Got it? Okay. So this is the last question for today. That for the vibrational Raman spectrum of N2, the selection rule under harmonic approximation, which will be that. Okay. So you have to find which one of the following, that what should be the value of delta V for vibrational Raman transition. You will be able to answer that, right? What should be the answer? What are the selection rule for IR or normal vibrational transition?
D mu by dx should not be equal to 0.
Selection rule. Okay. So what you are saying, du mu by dx is equals to 0. This is you are telling, right? Hmm? Okay. So this is the condition to show higher activity, right? Yes, you are correct. But in terms of wave number, you that this is known as gross selection rule. Okay. There is some specific selection rule which is,
Delta nu should be plus or minus
so this
1.
is delta V. Okay. This is delta V. This looks like new, but this is not new. This is delta V. Okay. And delta V is equals to, tell me.
Plus minus 1
Uh,
plus minus 2
uh,
and
and so on.
and
Okay, right? But
yes,
in the question, you are right. Exactly, you have said this right. For normal IR, this is correct. You are mentioning here what is this harmonic approximation. So just recall that whenever I have discussed about harmonic oscillator, I have told you that the condition for transition is for harmonic oscillator. What was the selection rule?
plus minus 2.
No, I am talking about this. Forget about this Raman. I am talking about your normal vibrational spectrum. There, whenever we have started this vibrational spectroscopy, we have first derived using this harmonic oscillator, right? There we have got the value of delta V, that is the vibrational quantum number will be changed by plus minus 1. Then we have used enharmonic oscillator approximation, and then using enharmonicity we have got this vibrational transition is anything possible. Delta V equal to plus minus 1, plus minus 2, all are possible. But in the very beginning stage when we are dealing with only this harmonic oscillator approximation, our selection rule was only delta V equals to plus minus 1, right? And whatever I have said you earlier, so what is the what you are talking about delta V equals to plus minus 2, right? So for Raman, this is not delta V, this is delta J.
Yes,
Okay, don't confuse among themselves. So delta J is just for rotational line, right?
yes,
J, whenever you will find any quantum number which is mentioned as J is calls for rotational line. V stands for vibrational line. Okay. So delta J is plus minus 2, which means your rotational levels will be plus minus 2 transition will be possible. But whatever I said, that your vibrational transition will follow the same rule as that of initial vibrational transition. And your initial vibrational transition says that under harmonic oscillator approximation, the selection rule will be delta V equals to plus minus 1. So for Raman, so what will be the selection rule?
plus minus 1.
Exactly.
And
So your for vibrational Raman, there will be the selection rule as the same as the vibrational harmonic oscillator. That will be delta V equals to plus minus 1. Okay. So if there was no mention of harmonic oscillator approximation, so for vibrational Raman spectroscopy of N2, what should be the selection rule? For harmonic oscillator, vibrational Raman, vibrational Raman will occur due to transition delta V equal to plus minus 1. But if there is no mention of harmonic oscillator, yes. So what should be the selection rule for vibrational Raman? What should be the delta V? If no harmonic oscillator, I am taking, I'm just only saying an harmonic oscillator. So what will be the selection rule then?
delta V equal to 0 plus minus 1
So in
plus.
vibrational spectroscopy, you will not get 0. Whenever you have learned this delta nu V equals to plus minus 1, 2, 3, 4, right? Right?
Yes,
So for enharmonic oscillator, your vibrational Raman will show this delta V will be equals to plus minus 1, plus minus 2, plus minus 3, etc. Okay, you got it? Since here harmonic of approximation is mentioned, so I am taking only delta V equals to plus minus 1, which was initially derived as the selection rule for harmonic oscillator, right? Okay. So have you understand all the answers that I have solved?
yes.
Okay, fine. Okay, so I'm closing the session. Done. If you have any problem, then you can tell me in the next, or I will upload it in the YouTube. You can also see it. Okay.
Okay, sir.
Okay.
Thank you.
Okay. Thank you.